Okay, so now I will discuss the mass and the volume flow rates and the relation between these two. So it is important. We are going to solve some problem for mass and the volume flow rate, and what is the relations between these two. You will see for many problem we need to use this. So let's try to understand this. Actually, mass flow rate is something, when we consider any problem, let's say a open system, so the mass flow should happen there should be mass interactions between the system and the surroundings, definitely at the system boundary. So the amount of mass that usually flow through the cross section of this system per unit time is called the mass flow rate. If I draw a control surface like this, let's say this is actually, instead of dotted I just put it as a solid line. So let's say this is the control surface, just forget about the other one. So this is very small section. I will consider this very small elementary part. Let's say this is actually very small section, elementary section, and we can say this is actually dA, the area for this small section. This is dA. Okay, so if it is the case, and let's say the velocity, this is actually the velocity vector, okay, v velocity vector, and this is actually the vn, the component. Anyways, so now what I'm trying to tell you guys, when a fluid, it is, let's say it is going out or it is just coming in, it could be both cases, right? That this is a control surface, so fluid can go out, fluid can come out. So usually they go through this this control volume. So we consider the very differential area delta A. So through this differential area, definitely we will have very differential mass flow rate, isn't it? Not a lot, because this is very small area. So we can say the differential mass flow rate through this very small section, small elementary area DSE, it will be proportional to the area. That means, so what I said, the differential mass flow rate to a small area, okay, will be proportional to this area. That means the mass flow rate will be higher if this area is higher. The mass flow will be lower if the area is lower. So let's say, kind of, if we consider this is some lake, so if it is higher, then there will be mass flow rate. If it is lower, then it should be, it is smaller, then it should be lower mass flow rate. Yeah, that we know. So from the theories, what we know, guys, the mass flow rate, the differential mass flow rate, let's say dm or delta m, the differential mass flow rate, it is actually proportional to this area dA, this cross-sectional area, and let's say here we have the fluid. So the density of the fluid, how dense it is, the density of the fluid, and the velocity Vn. So this is actually the formula. The mass flow, the differential mass flow rate through the small elementary area of this pipe or of this duct, it is proportional to that area itself, the density and the velocity. So this delta over d, we usually say this is a differential section. Now if we have a system, it is this is actually the total differential mass flow rate. But if we want to calculate the total mass flow rate, so what it is, total mass flow rate means m dot, right? So usually m is mass, so if we put dot, this is, we say mass flow rate, b is the volume, if b dot means the volume flow rate. Anyways, if we want to get the total the total mass flow rate, what we need to do, guys, we need to do some integration, isn't it? We need to do integration. So it should be rho Vn dSE, isn't it? It was the differential part, and we now did integration. So if we do that, then we can easily cancel out this term, and it will be, you see, m, the mass flow rate, it is equal, we can say rho Vn dAc. This is for that small cross-sectional area, right? So we can define this as equation A. So this is very appropriate expression. We can accurately calculate the mass flow rate by using this formula. But as an engineer, you will always try to find out something more efficient, more simple, and not time consuming. So this contains some integration. We need to do some integration. So we need to follow a lot of iterative process. It is time consuming. So what we can do, maybe we need to find out some other approach instead of this integration. You know what I mean? I said this integration, it will be time consuming. So we don't want to do that. We need more easy solution. So to avoid this, we will introduce a new concept. This is the average velocity. We will use the average velocity throughout the pipe, and by using this average velocity, we will calculate the mass flow rate. So if you see here, guys, some of you are doing maybe heat transfer in this subject, or some of you did fluid mechanics. This is a pipe, and it is showing actually the velocity profile. This arrow symbol, it means the directions and the magnitude as well. So you see here, this arrow, it is highest, then you see it is smaller, then it's increasing. So this length, it's actually telling you the magnitude as well, the direction and magnitude. So what you can see, if you agree with me that this arrow, it's actually showing the magnitude, the flow magnitude as well. So that means here in this section we have the zero velocity, because you see it is the pipe wall, pipe is not moving. So that means the velocity here, it is zero. So when the fluid particle touches this wall surface, the velocity will be zero. So that means it has some inertia. When we will move from the surface to this is actually the center, then you will see the velocity will increase gradually, and it creates a profile like that. It is called the fully developed flow, and the velocity will be maximum at the center. So we defined, okay, at this point, this is actually, if it is the maximum velocity, if it is the minimum velocity, we said, okay, this is the average velocity, V average. And we define this average velocity. This is very high thought concept, like the boundary layer formation. I'm not going to discuss boundary layer formation. Maybe your lecturer for fluid mechanics and heat transfer, they already discussed the boundary layer and the fully developed flow. So I'm not going to discuss that, but during the lecture I will try to discuss a bit more. So we can define the average velocity, V average, it is equal, the integration of the velocity component and the cross-sectional area, and it is the integration of 1 by AC. So this is what I said, guys. Here it is actually the average velocity. So we said this is the average velocity. Look, can you relate this this average velocity and this one here? Especially when we have many engineering applications, the definition of the compressible flow and incompressible flow. So we have many engineering applications where the density is uniform. So especially for this problem, let me check whether I have some or not here. Okay, for many engineering applications, we know the density could be constant. So previously we had the mass flow rate, it was the AC, that means the surface area, and rho Vn dAc. So it was the equation, and we got the average velocity. The average velocity, it is 1 over, this is the definition of the average velocity, Vn dAc. So now what I said, we have many engineering applications, especially for the compressible flow. Sometimes we can say the density is not changing. So if I put the density out of the domain, it will be AC. This is Vn dAc, right? We can write this. So if I look here, guys, I'm just doing parallelly here. Can I write it like this? V average into AC. This is equal integration of Vn dAc. DAC. Look here what I did. I just did some cross multiplication. So V, the velocity average and the cross-sectional area, it is equal V and DAC. So now can we substitute this integration, this value here, V and DAC equal this here? We can. So we can write it as rho into the average velocity into the cross-sectional area. So that means we got, guys, the mass flow rate, it is actually the density, average velocity, and cross-sectional area. So as an engineer, you will always try to find out something easier. So we just skip this integration here. So we're not going to do integration. We will instead use the average velocity. So that's actually the average and mass flow rate. Now we know the volume flow rate. So we need to calculate the volume flow rate. So volume flow rate, if I go to the next slide, so we can say the volume flow rate. The volume flow rate is, we can say this is the pipe, okay? This is a pipe. So we have the flow going here. And if we consider, a small, let's say this is a small section, let's say this is actually AC, and the velocity is, here we have, this is the average velocity. We know how can we calculate the volume. So we are not going to use that integration, so we are going to use the concept of the average velocity. So if we multiply, guys, here, I'm not showing a lot of calculations. So for volume flow rate, we know the volume flow rate definition. It is equal the integration of this, this cross-sectional area into the volume, the velocity Vn and DAC. We already know this Vn DAC, it is equal the average velocity and cross-sectional area, right? So we can say, okay, the volume flow rate is the average velocity and cross-sectional area. Now we got the mass flow rate, it is equal, the rho, the average velocity and the cross-sectional area. We got the volume flow rate, it is equal the average velocity and the cross-sectional area, right? So now what is the relation between mass flow rate and volume flow rate? How we can develop a relations between mass and volume flow rate? Guys, can we just simply substitute this V average AC equal V dot here? We can. So it will be mass flow rate, it is equal density into volume flow rate. Okay, so this is one relation. In other words, we know the reciprocal of the density is the specific volume. So specific volume V, it is equal to 1 by rho. Okay, we know this expression. Or what we can say, guys, rho, it is equal 1 over the specific volume V. So if we substitute the rho equal 1 over V into this V dot, that means it could be another expression. So finally the relations between mass flow rate and the volume flow rate, we can say, could be this. So in different problem we will use this expression. So what I said, guys, in this video I tried to explain what is mass flow rate, how we will calculate that, what is volume flow rate, how we will calculate that, and the relations between the mass flow rate and the volume flow rate. I hope you understand this. This is the first time, maybe if some of you may find this is a bit difficult, so attend the lecture and it will be more clear.